Okay, so let's continue on our adventures with categorical dependent data. And to start things off, let's start with the good news that inside of structural equation modeling software, it's pretty easy to tell the computer program, hey, we've got categorical data that's dependent. So if you're doing that inside of the Latent system, you need to tell the computer that these are ordered data. And if you're running the Latent system, you need to have an ordered statement in, and that will say, oh, then these are ordered. Similarly, if you're playing with M+, that's also pretty easy. You can come back into a program. So for example, if you have an exploratory factor analysis and you want to have, excuse me, let me admit everybody. If you, okay. Similarly, if you're doing an exploratory factor analysis, you have the names of the variables in your study, and then you add underneath that a line that says, oh, and here are the variables that are categorical. And across both of those platforms, it doesn't matter. Some of these can be continuous, some of them can be categorical, you can mix them up. Similarly, if you're playing with Amos, it's very easy to run it. We need to talk a little bit about that. But if you have a dependent, a manifest variable that's categorical, inside of that, you'll have to come in and turn on Bayesian estimation. And walking through how to do a Bayesian analysis is a little more work than what I can just hand wave here. But that's, the good news is we can get there. The issue that we're talking about now, though, is exactly what is going on. And the reason that you need to know a little bit of exactly what these computer programs are doing is you will have different assumptions about how those categorical variables get handled. And if you're looking at something like longitudinal data, you need to be able to tell the computer program how to override some of those defaults. In this handout, I didn't do a lot of talking about longitudinal data with categorical, and that's mainly because there's a really nice book, Longitudinal, let me grab it here. Longitudinal Structural Equation Modeling by Jason Newsom has a lot of really nice examples. So, and also this particular chapter that I wrote was long enough as it stands. The last time that we had talked, I had talked about the fact that there are two underlying latent response variables that we often think about, the normal and the logistic curve, and those have some formulas for them. And the normal distribution we all seem to think we know. The logistic distribution also has this really nice mathematical form. The logistic function also has a relationship to something called the odds ratio, and we'll get to that when we get into the look under the hood a little bit more with the logistic curve. The next thing to talk about, though, is how are we going to use categorical data, 0, 1 data, or 0, 1, 2, 3 data, or a 5-point Likert scale? How are we going to use that to use the categorical nature of the variable to inform us about the underlying continuous distribution? And the central idea here is a threshold. Turn off my heater down here. And what we're doing here is we're assuming that there's a given proportion of our 0 and variable that we observe, and that corresponds to some point on this distribution. So a 0.5, if you have 62% zeros and 38% ones in your data, if we use those formulae above, that's going to correspond to a 0.5 value on this logistic curve. And if we're using the logistic curve, we're going to refer to that as a logit. That's just a term of art. And downstairs, if you like the normal distribution more, if we have 62% below the point and 38% above, that corresponds to a z-score of 0.3. And when we're using the normal distribution as our reference curve, we're going to call that a probit. So now we're going to use this idea of some kind of a threshold as indicating where you are on that variable we don't have in the context of a regression. So although you might think that the probit is easiest, the logit has some math properties that make it a little bit easier to understand here. So what I've drawn here is the cumulative distribution function for the normal and logistic curves. And so as we're going from -3 up to +3, you'll notice that as I go up, I'm going to eventually get to this cutoff. So rather than this distribution, which is called the PDF for the probability density function, what we're looking down here at is the cumulative distribution. So this will answer the question, what proportion of people scored at or below this particular value? And the reason that we're looking at that is the value here of 0.62 corresponds to a value of 0.3 for the normal and 0.5 for the logistic. And if we're playing with the logistic curve, this particular cumulative distribution function has a nice formula. So as you can see, this is pretty easy. If you're trying to get at the cumulative distribution function for the normal, it involves an integral. So it's a little bit more mathematically complicated, which is why I thought it's just easier to talk about the logit curve for the moment. So if we're evaluating this curve, we've got to, to get this cut score off here for the normal distribution, I've got to evaluate this integral. That's a little more messy. And in most applications, it's easiest to use the standard. Oh, here comes somebody, right? It's simplest to use the normal for the data. In longitudinal data, as I mentioned before, you're going to have to start thinking about not a mean zero variance of 1, but you're going to move around that shape of that distribution. Was there a question? No, or maybe just a random mic not muted. Okay.
I have a question.
Yay.
Just to clarify, speaking about the dependent categorical variable, we know that in structural equation model, a variable which is dependent can be independent variable also. So
Yeah, well,
when you talk about
having a categorical independent variable isn't a problem. So,
okay, so
all right, yeah, go ahead.
Yeah, so I would like to clarify that it's not including that kind of variable when you talk about categorical variable.
It's not including the what?
That kind of variable which is dependent but at the same time become independent variable for another path.
Right, if it's dependent once, then yeah, we have to start playing with thresholds. So if you're saying X causes a categorical variable and that categorical variable in turn causes something else, is that what you're saying?
Yes.
Yeah, then we need to play with thresholds.
You need to play with what, sorry?
We need to do this latent response variable formulation.
Oh.
So if you just have a categorical variable that's a predictor, you're right in saying that's not an issue. We just modeled that the way it is. But if it's being predicted inside of a structural equation model as a dependent variable, then we need to use either a logit or a probit link function. Is that
okay?
Okay. All right. So let's now take a look at what a regression looks like with this link function. Well, here's where the logit comes into play. So I'm going to say that my predicted y-score is going to be the natural logarithm of some proportion divided by 1 minus that proportion. And that's the thing that I'm going to predict. So my y predict is going to be the natural logarithm of this odds ratio. That's, in words, what that's saying. And if I want to get the probability that y is 1 based on my predictor variables, it's going to be this formula down here. So rather than having a prediction that's 0 and 1, we're going to have a prediction of the odds that we will have a 1 divided by the odds that we won't have a 1. And it helps to do a little example. If we didn't have any predictor variables in the model, but we only had a regression intercept, and we had that 0.5 threshold that we had up on the figure I just showed you, that's going to return for you the base rate proportion in the data. So when I have predictor variables in here, the interpretation of this regression intercept is the same as it is in a regular regression. It's going to represent the natural logarithm of the odds ratio associated with the scenario where all the predictors are 0, that is the y-intercept. Now, often the y-intercept based on raw data is not a value you're going to have because the predictor variables are positive numbers and the y-intercept doesn't correspond to values that you actually have. And so for this reason, rather than using the adjoint matrix, the column of 1s is sometimes adjoined to the deviation score version. And the reason that you do that is the odds ratio, the intercept then corresponds to the natural logarithm of the odds ratio of the centroid of your predictors. That is, it's going to correspond to the odds of diagnosing divided by not diagnosing, or having a 1 divided by having a 0 for the mean across all your predictor variables. And in the more general case, where you have lots of predictors, the regression rate associated with the continuum variables indicates an increase or decrease in the odds ratio. So that odds ratio, kind of one of the takeaways about this is that odds ratio gets you into something that in theory could go from minus infinity to plus infinity, rather than just a 0-1 variable. So if you're doing things with the probit link function, it's the same thing. It's just that the math is a little bit more complicated because you're going to be talking about this integral going from minus infinity up to a particular value of xb. So, that's kind of the trick. Now, the other thing about categorical data to talk about is that there's lots of ways to actually deal with the fact that your dependent variable is categorical. And Lavon, M+, other software packages will make defaults. But depending on how big of a data set you have, depending on whether missing data is an issue, and depending on your computer resources, there's different ways to do this. So, not to get into the technical discussion, but let me tell you, the bottom line is MLR is often preferred if your latent response variable is appropriate for your research question. So, and that's because MLR estimation, maximum likelihood with robust standard errors, is robust to your ideas about missingness in the data. Because some of the other ways of dealing with categorical data deal with a pairwise estimation of what that correlation is. And while that approach is going to be useful if you have a large data set, it's, there's not necessarily all the guarantees that you will have estimates that will have some desirable mathematical properties with respect to the thought that there might be missingness underlying your data and the ability to estimate the data set. So I'm trying to start off with the conclusion that we're going to end up with before we get into the guts of this. Weighted least squares with mean and variance adjustment is not as computationally intensive. And for that reason, that's what M+ and Lavon do. It has the advantage that it can accommodate a latent response variable in non-standard form. That is, whenever I want to say that my latent response variable has a mean of 0 and maybe a variance that's not 1, I can do that with WLSMV. When I'm upstairs doing MLR, at least in the current iterations of Lavon and M+, I must assume that my latent response variable has a mean of 0 and variance of 1, which is the standard form. And there are other ways of dealing with categorical data that are adjustments. So let's just kind of talk about how we handle continuous data, categorical data, and estimate what correlations are. If you're doing an exploratory factor analysis inside of R using FA, or if you're doing a factor analysis inside of SAS or SPSS, frequently you'll find people saying, I'm going to estimate pairwise correlations. So what they'll do is they'll take the proportion, say you have two categorical variables, they'll take the proportions of zeros and ones on each of those and use the threshold cutoffs on those normal distributions to get an estimate of what the correlation coefficient must be between those two categorical variables. And it's easy. I mean, it's straightforward, and the software does that for you. So if both of your variables are categorical, that's called a tetrachoric correlation. And if we're playing with that, my base data that I'm going to be using are the frequency counts for the zeros and ones across the two categorical variables. And here's the formula for it, where the estimated correlation coefficient is gamma -1 divided by gamma +1. And in that case, gamma is going to be the number of, the diagonal elements divided by the off-diagonal elements multiplied by each other, all to the pi-4. And if 0, 1 or 1, 0, these things, if either of those are 0, I'm going to report out the correlation as 1. And if what's on the diagonal is 0, this one or this one, I'm going to report out the correlation as -1. Now, I did some Googling because my daughter talks about millennial magic, and to try to get an idea of the guidance that you would think you have if you just went out and say, I have categorical data, I want to do a factor analysis. Nobody ever mentions this property of the tetrachoric correlation. But if you're using a small data set and off-diagonal elements are going to happen, quite a bit, having zeros just because you don't have a lot of data, or something on the diagonal is going to be 0. Notice you're going to end up with correlations of either 0, 1, or -1. Those are your only 3 options. There's another formula that I just put in because, when the Earth's outer crust was cooling and I was a graduate student, that gave you a delta And you can calculate that correlation using this alternate formula as well, but you have the same thing. So I walk you through an example here of the cross tabulation and show that yes, indeed, with these counts, this gives you that correlation coefficient of 0.83. So if you have one categorical, sorry, if you have more than two categories, that's called a polychoric correlation coefficient. And it's the same math using two thresholds, because now I've got 0, 1, and 2 as the three levels if I have that. Biserial correlations are ways to get an estimate of the correlation between two variables if I've got one is dichotomous and the other one is continuous. And if we're playing with that, this is the formula. And mean of y1, mean of y0 are the two means of the people in the 0 and 1 group. And I can simplify that out to this. So that gives me the correlation between those two variables adjusted for base rate. And I don't have any words of wisdom on that. Biserial correlations are not going to have that property of going -1, 1, and 0 quite as much because of just the formula that's involved. And then I walk you through an example of how to do a biserial correlation. And the same way, polyserial correlations are just involving three levels. So, it's a little bit statty and mathy nerdy, but now you've seen the formulas, and not only just to look at the formulas, but there are a few little cautions here and there about those. Now, inside of your program, our computer program is going to go in and generate for us a correlation matrix. So what people sometimes do is, rather than, if you're playing inside of M+ or Lavon, you're just going to say, hey, these variables are categorical, deal with it. If you're using other programs like the FA program, you're going to have to go out and generate this correlation matrix based on your data and feed that correlation matrix into FA. Now, there is old software out there. Lizrel is like the first structural equation modeling program out there. There was a program called Prelis that did that for you, and then Prelis generated a correlation matrix, and that then passed along to Lizrel for SEM analysis. Now, let's talk a little bit about what goes on when people do analyses. Sometimes you'll find researchers, maybe your advisor, who says, well, what I'm going to do is I'm just going to take the correlation matrix and stuff that into the factor analysis program, because I don't want to do all these fancy pairwise adjustments. And that's going to underestimate the association between two variables. So, this is an argument for using this software to produce a correlation matrix that does take into the categorical nature of the data. There's some reasons, though, to be a little bit cautious about that. So, as I mentioned, empty cells are a problem for a tetrachoric. And if you're playing with a small sample size, you're going to be having perfect or zero correlations in there. It's going to be kind of an issue. And especially if you're playing with small samples, if you make one adjustment to the correlation between variables A and B, and another adjustment for the correlation between A and C, and yet maybe another adjustment for B and C, there's no guarantee that the matrix that you get out is necessarily going to be a full rank. In other words, there's no guarantee that you may be even able to invert that matrix. So in practice, if you've got kind of a small data set and you're going to be making these correlation matrices, you might need to group some sparse categories together with more frequently occurring values in order to get an analysis that's useful. So in words, what I mean here is if you have, say, a smaller data set, 300, 400 people, and you have a Likert scale, then maybe you might want to collapse, say, the 4s and the 5s together so that you don't have a very small number of people in each of the levels of the category. And, in other situations, we've got a huge sample and none of the individual categories are rare events. Doing these correlation pairwise adjustments and feeding it into a factor analysis might be just fine. So I've talked rather a bit about this strategy, but my objective is, do you understand what pairwise correlation estimates are and making a correlation matrix? And, and if you are interested, you can come back up and use the software that I mentioned at the top of the, now where is it? That will get you into making those correlations. Right. So how did I get down here? Oh, I'm in the wrong accident. Clicked on a link. Apologies. So the next thing to talk about is diagonally weighted least squares. And it kind of goes by, we've met this before, back in page 164. And one of the issues with diagonally weighted least squares when you've got categorical data is you need to adjust that for the mean and variance of the variables. And that is called WLSMV. And as I mentioned, this is the default for M+ and Lavon. And in WLSMV, you're only dealing with the probit length function. And so what we were talking about up above at the top when I showed you that exploratory factor analysis program, that's going to be doing WLSMV. And inside of M+, that's going to give you some robust standard errors and a mean and variance adjusted chi-square statistic. So what I'm saying here is, if you just did WLSMV and you looked at your parameter estimates and then looked over at the regular old standard error, that's going to be misleading. So M+ does an adjustment for that to give you a better standard error. M+ also gives you a chi-square statistic that's adjusted. Now, the thing about that chi-square that comes out is we can't compare chi-square statistics across our models using a chi-square difference test. So inside of M+, there's a command called the Diff Test option that you need to use in order to make a comparison between two models. So in words, what happens is you run your base model and you save the output of that to a file. And then you run your target model, and then you tell the computer program, oh, and look over here for the information about the base model, and it then calculates the chi-square difference for you. So and when we get more into program examples, we'll talk about that. Another way of taking into account categorical data is to do maximum likelihood with robust standard errors. And that uses something called a sandwich estimator to give parameter estimates for you. And ML estimation is a full information estimation technique. So What this means in words is that the earlier technique, the earlier approaches that we had are doing kind of sort of a pairwise adjustment thing. But in maximum likelihood, I'm going to take all of the information across all of my variables that involve, say, a categorical variable, and use that to get an estimate of what the threshold should be for that particular model. And so if you can get away with it, so to speak, if you have a data set that does not consist of hundreds of thousands of people, maximum likelihood is probably a preferable way for you to estimate the model. Now, maximum likelihood is more computationally intensive, but if you're willing to wait, it's not a problem. If you read about it, maximum likelihood is more efficient than WLSMV. And what statisticians mean when they say that is the estimated parameter is going to do a better job of getting you toward the population value than WLSMV. Now, that issue of efficiency is, again, not so much of an issue when you have a large sample, because at that point, if you have lots and lots of people, you will efficiently be getting to it. But if you have a smaller data set, maximum likelihood is preferable to WLSMV for that reason. Second, because MLR is a simultaneous approach, that is, it estimates one threshold across all the values, it's more appropriate when data are missing at random. And the other nice thing about ML is when your latent variable distribution is skewed, it performs better than WLSMV. And skewed latent variables happen quite frequently, at least in psychological data. If you're dealing, for example, with student ratings of teacher instruction, that's a very skewed variable, because frequently, God bless students, they're terribly charitable. They say, well, it wasn't entirely awful, and you have to be really bad to score bad. So that has a large negative skew. Similarly, if you're looking at problem behaviors or problem attitudes like dogmatism or authoritarianism, those things are also skewed because a relatively small number of people engage in a problem behavior or hold really problematic ideas. And as for WLSMV, the robust standard errors work well for sample sizes provided you have at least 250. And these are working better than the unadjusted full information estimates. So that was my little, over the summer, review the literature of estimation material. So the sad part, though, is you still can't compare the chi-square statistics out of your ML model. And I give you the website to go, take a look at calculating those statistics from a printout from two models. When you're doing the MLR estimate, it's going to default to logit inside of M+. It's possible to specify a probit length function as well, but in both of those cases, as I mentioned before, if you're doing maximum likelihood, you have to be looking at the standard mean zero variance of 1 probit distribution. And this strategy, this is just me linking to something else that I read, but the strategy is kind of similar to an article that was done in 1979, where they did one threshold across everything and then estimated the response. So to summarize a little bit, it's helpful to notice, as in the discussion of pairwise, the ability to successfully estimate threshold correlations depends on your sample size. And I made this little table based on things you need to think about. And it's adapted from a table that Muthen put out. So if you've got, if your model has an awful lot of factors out there, weighted least squares and using a Bayesian analysis works fairly well. And if you have a lot of variables, maybe maximum likelihood and Bayesian estimation are preferable. If you have an awful lot of subjects, weighted least squares is best, because as I mentioned before, you don't have to worry about efficiency. And if you have a small number of people in your study, maximum likelihood and Bayesian estimates are probably good. And if you're looking at statistical efficiency, ML and Bayes are preferable.
I have a question.
Yeah.
On the table, what if we have large amount of factors but a small number of subjects?
I would say if you've got, just making up a number, 300, 300 to 500 people is 300 would be small, I would think. It kind of depends on how many variables you have too, but the reason that maximum likelihood and Bayes are preferable is they're going to go through and do the estimation based on properties of each individual record. And weighted least squares comes out and calculates that correlation matrix for you. And as such, it only has to work with that correlation matrix. So if you have hundreds of thousands of people, it's better.
So small number of subjects refer to the number of subjects is around 500 or 300.
Yeah.
They are still small. So what about the number of factors? What do you mean with large number of factors versus small number of factors?
Well, he doesn't really talk about that. And it's a little bit hard to say what number of factors is large, because it also depends on how many variables you have. But if, just making up a number, I would guess if you're talking about more than 10.
Okay, I see. Thank you.
And so, just to kind of talk about how this has affected my life, very frequently there are data sets with large numbers of people, like ad health or population surveys. And it's also an awful lot of diagnostic information. And so we have a lot of factors in those models, and we have hundreds of thousands of people. And you would, I can tell you from experience, you'll be waiting several days, even on a very well appointed computer, for the maximum likelihood solution to be coming out. So that's, but the reason that I'm going through this is when you fire up Lavon or M+, it's just going to say, I'm going to do weighted least squares because I have no idea, what your data are, how many factors you're going to tell me. So here's my default.
Oh, I see.
Now, okay, as I mentioned, before, missing data is a little bit nicer in maximum likelihood and Bayes. And you can also, to some extent, test the latent response variable structure. That is, I can play in models that permit it. I can look at, is the mean and variance the same or different over time? And that's fine. Ordered polynomous variables are much easier to do with weighted least squares. And these negatives for maximum likelihood and Bayes are not disqualifying things. It's just that it's going to take a little more computing. And being able to handle Haywood cases is really easy inside of Bayes, because Bayesian will never allow an error variance to become less than 0. If you have 0 cells in your data, that's kind of a big, as I mentioned before, that's a big problem with weighted least squares, because you're going to get 1s, -1s, or 0s, depending on where those 0s fall. And with maximum likelihood, that's not so much of an issue. And if you're estimating residual correlations, it's a lot easier to do in weighted least squares. And depending on your model, it may or may not be a problem in Bayes, but having residual correlations in maximum likelihood is kind of hard to do. So, as I wrote this past summer, I kept thinking I'm going to put, the best foot forward of giving you the answers, But at the top of the chapter, I talked about WLSMV being fairly good and maximum likelihood being also pretty good. Bayesian analysis is itself probably its own class. And Ed Merkel teaches a nice Bayesian class, and there's also Bayesian classes in the statistics department that you can take. There is a Bayesian statistics program called Blavon that Ed and Yves have worked on for doing Bayesian statistics and using Lavon syntax. And as I mentioned before, inside of Amos, it's pretty easy to turn on the Bayesian estimator. I'll probably do that and show you what goes on. And that's what I talked about down here. So, I realize this is sledding through a lot of details, but let's talk about the variance of the latent response variable. So the WLSMV estimator comes in two versions, depending on the scaling choices of your response variable. So inside of the program, in other words, the reason I'm going into this is when you look at a Lavon or an M+ program, you're not going to be able to go in and immediately take a look at the mean and variance of the latent response variable. For kind of some mathy reasons, they come out and talk to you about this model being estimated with something called a scaling factor. So this is why we're getting into this discussion. And it's a little bit hard to write it all out. And I played around with it and I thought, there's no earthly way that I can give a systematic presentation to it. If you want, there's a reference that you can take a look at. But let's start with a simple example. Here's a categorical dependent variable, which has an indicator on a factor. So now I'm talking about a structural equation model. My variable, my dependent variable has a 0, 1 number, and that is serving as an indicator of a factor. Well, so the variance of my latent response variable is going to be this bit. That is, it's going to be the loading that I'm estimating squared times the factor variance. In other words, just by the tracing rules, the variance of my latent response variable is going to be the loading times the sling times the loading, plus, and there's this little bit of math term over here, pi squared divided by 3. And the reason that we're doing that is the standard deviation of the logistic distribution is pi divided by √3. So what we're looking at here is loading times variance times loading plus standard variance of what's left over for the latent response variable. And similarly, if I'm playing with the probit function, the variance of the latent response variable is going to be the loading times the variance times the loading plus 1, because my probit standard normal distribution has a variance of 1. And here's, now why you care. In WLSMV, there's two ways to estimate this response variable, called delta and theta parameterization. And you can choose these as just a command inside the analysis section of your M+ program. Now, for some mathy reasons, the default behavior in M+ is to do delta parameterization. That's just because the program runs a little better. If, however, you want to have an error variance in your model, such as might occur, for example, if you say, I want to do a factor analysis, and here's one categorical variable and another categorical variable, and I want the measurement errors to have a covariance, you'll need to specify theta parameterization. So, often what people will do is they'll say, well, here's my SEM, I have some categorical variables, and I want to say that these two error variances are correlated, and the program won't let me do it. Well, the fix to that is to say parameterization equals theta. And delta parameterization is also called marginal parameterization. Happens because we're constraining the residual variance to 1, because the underlying normal distribution is thought to have a unit variance, and it estimates the variance of my latent response variable, by this command. So, the variance of the entire latent response variable is this part plus the number 1. And under theta parameterization, the variance of the entire distribution is set to 1. That is, this is set to 1, and I'm going to come downstairs here and estimate the variance downstairs. So that scaling parameter down here is what's used to make the latent response variables have a total variance of 1. And that's the scaling factor is used to calculate the standardized estimates. So, it's a lot of blood, sweat, and tears with a whole bunch of math and a lot of terms, but it's helpful now to finally talk about an example. So I don't have much time, but we'll get into it and continue on. If I'm doing a single predictor logistic regression, for example, the math is exactly the same. So in one example I might be interested in looking at is, do you or do you not drink 5 or more drinks in a sitting? And I made this little plot with this bit of R code that gives me the low S regression and a curve. And that, what I'm looking for here is hopefully a straight line. And if I'm fitting this to a logistic model, here's the code that you would do it if you were doing it inside of M+. Well, here's my data. Here are my variables. Here's a categorical variable. And what I did in here was to take the high values of the enhancement reasons and collapse them across. So if you score higher than 17, I made it into a 17. And the reason I did that is, look up here. This is 15, 16, 17. It seemed like this area over here was more or less flat. So if I want to get a good estimate of the logistic odds, I'm trying to get straight lines when I do a regression. So that's the reason that I use lowest regression to suggest a transformation of the continuous variable. And I centered my continuous variable so that my intercept looks like the mean of the centroid. So at the end of the day, the intercept of this variable is going to correspond to the base rate proportion of 5 or more drinks in a sitting in the population I'm looking at, right? So I'm going to stop here. What's going to come is, how to change this and do MLR and WLSMV, and then we'll talk about the printouts come Wednesday, right? Oh, okay, thank you.